Good morning, one and all. Myself, M. Premchandar, Assistant Professor in Malaradi Engineering College for Women. Today we are going to discuss about a topic, traveling salesperson problem using dynamic programming. So, in the dynamic programming, what is the dynamic programming? So, earlier we have studied about greedy method. So, greedy method as well as versus dynamic programming, both methods are used to solve optimization problems. Both methods are used to solve optimization problems. What is optimization problems? Okay, for minimum results, for for getting minimum result or maximum result, we are going to solve these problems. These are nothing but optimization problems. So what is the greedy method actually? Greedy method always looks for a feasible solution. Greedy method always looks for a feasible solution, and dynamic programming working on the principle of optimality. Okay, optimality principle. Dynamic programming always works on the principle of optimality. So what is the dynamic programming? So dynamic programming is an algorithm design technique for optimization problems, often minimization or maximizing. So it is also like divide and conquer method, and dynamic programming solves the problems combining solutions to the sub problems. So it is like unlike divide and conquer, sub problems are not independent. So here the sub problems will share the sub problems. However, solution to one sub problem may not affect to other sub problems. Okay, this is known as the dynamic programming. So, and here in the dynamic programming, so we will also consider the overlapping sub problems. Overlapping sub problems. Suppose, for example, if you are considering the Fibonacci series, like n is equal to 0, 1, 2, 3, 4, 5, 6, and the value of f of n, for n is equal to 0, the f of n is equal to 0, and for n is equal to 1, the f of n equal to 1. For 2 it is 1, then for n is equal to 3 it is 2, for n is equal to 4 it is 3. So we are considering here the Fibonacci series. Suppose, for example, f of n equal to f of n minus 1 plus f of n minus 2. Then suppose if you are considering f of n equal to 3, so f of 3 equal to f of 3 minus 1 plus f of 3 minus 2. So by considering, you are getting here f of 3 equal to 2. So here in the dynamic programming, the computation starts from solving sub problems in a bottom up fashion, as well as top down fashion. So here storing the solutions to a sub problem in the first time, we are going to solve the sub problems, the solutions, we are going to store in a table. So looking up the solution when sub problems encountered again, we can use that value from the table. So what are the steps we are following in dynamic programming? So characterize structure of an optimal solution. So defining a value from optimal solution recursively, then compute the optimal solution values either top down or bottom up in a table. So construct an optimal solution from computed values. So what is the principle of optimality in the dynamic programming? So it states that an optimal sequence of decisions has a property that whatever the initial state and decisions are, the remaining decisions must constitute an optimal decision. An optimal decision sequence with regard to the state resulting from the first decision. So the principle of optimality states that, so whatever the first decision we are considering, then the sequence of optimal decisions all over we are calculating to get an optimal solution. So if you are considering the traveling salesperson problem, actually what is the traveling salesperson problem? So a traveling salesperson is advertising his product. Suppose if you are considering some number of cities, like Bombay, Hyderabad, okay, Bangalore, Karnataka, like. Suppose if you are considering 4 cities, okay, from one city to other city, he is going to travel, okay. So here, actually, what is the main thing here? So he has to cover all the cities. He has to cover all the cities as well as whatever the starting point, whatever the starting point is there, then ending point should be same. Whatever the starting point and ending point should be same. Suppose if you are considering the 4 cities, like, okay, if you are considering 4 cities in a graph as 4 vertices from starting vertex to, okay, starting vertex to all covering, by covering all other vertices, he has to reach to starting vertex, okay, where he started. From there only he has to come back again. So here, suppose if you are considering a graph, here how many number of vertices we are having? 4 vertices. 1, 2, 3, 4. So suppose the traveling salesperson starting from vertex 1. So what are the other possible uh, vertices he may visit? So suppose the starting vertex, okay, he is going to start at 1. So other 3 vertices we are having here. Remaining, how many remaining vertices we are having here? 3 vertices. 2, 3 and 4. So this is a brute force method. Suppose, okay, by looking this diagram A, okay, A, B, C, D. So from starting point A, so what are the other three choices he is having? So B, C, D. Suppose, okay, he moved to B. What are the other 2 choices? C and D. Okay, now suppose he moved to C, B and D. Suppose, okay, he is having the other choices. Suppose he is moving to A to D. So what are the other 2 choices he is having? B, C. Suppose A, B, C he may visit. Then what is the remaining vertex? He has to move D. Okay, na, like A, B, C, D. Then A, B, D, C. A, C, B, D. Okay, A, C, D, B. Okay, D, B, C. A, D, B, C. A, D, C, B. So here the main point is from whatever the vertex he started, so ending should be that point only. So after considering all other vertices, he is moving to the same vertex, which is nothing but A. So this is a brute force method. This is a brute force method. What is a brute force method? Trying out all possible conditions, trying out all possible solutions and pick up the best one. Pick up the best one. So here, suppose for example, if you are considering this graph, so this is a bidirectional graph, A to B and B to A. Suppose 1 to 2, 2 to 1, and 1 to 3, 3 to 1, 1 to 4, 4 to 1. So here costs are different. Suppose 1 to 2 is, okay, like 10, then 2 to 1 is 5. So how it is possible? So whatever the distance from 1 to 2 is same, as well as 2 to 1 also same. So here we are considering the cost. Considering the cost. So suppose the cost is 1 to 2 is 10. So he may visit 1 to 2 by car, and 2 to 1 he may visit by bicycle. Like this, okay, we are going to consider the costs. So here suppose, okay, for this diagram we are drawn a cost matrix. Okay, like I think all of you know the cost matrix. So diagonal 1 to 1, 2 to 2, 3 to 3, 4 to 4, all zeros. Remaining are the costs we are having here. So yeah. So in the brute force method, if you are considering this diagram, after completion of all the vertices, okay, he has to visit the same. He has to visit to same position, okay, where he started. He has to reach that position only. So suppose here DC, suppose if you are considering the values 1 2 3 4 here, so starting vertex is the 1. Starting vertex is 1. So here the G of, okay, by using the dynamic programming approach, so G of 2 comma pi, G of 2 comma pi means 2 to 1. 2 to 1. What is the cost here? 2 to 1, 5. 3 to 1, 6, 4 to 1, 8. Like that, okay, we are going to consider. So here the formula is g of I comma s. G of cost of I comma s. I in the sense starting vertex. Yes, what is the capital S here? Okay, like all set of vertices. All set of vertices. So here, g of I comma s equal to minimum of cost of I to j. Cost of ij. Ij in the sense, so starting vertex is I to j, next vertex, he is going to visit the vertex. So cost of j comma in the sense, so I to j, suppose I is equal to 1, j is equal to 2, say I to j, say up to 1 to 2 he visited, from 2 to remaining vertexes, okay, he has to visit. So j belongs to set of vertices. So suppose here mod is equal to 1 if you are considering, so cost of 2 comma 3 means, okay, 2 to 3 he is going to travel. 2 to 3 he is going to travel. Then what is the formula here? C cost of 2 3 plus g of 3 comma pi. So what is the cost of 2 okay, 2 3 9. Then g of cost of 3 comma pi, how much? 6. So 9 plus 6 15. Like that, okay, we are going to consider all, we are going to calculate this one. Okay, 2 to 3, then 2 to 4, 3 to 2, okay, 3 to 4, 4 to 2, 4 to 3. Okay, like that we are going to calculate. Then mod s equal to 2. Mod s equal to 2, if you are considering, okay, cost of 2 comma 2 of 3 comma 4. So in this also we are going to calculate cost of 2 3, then cost of 2 4. So from this we are going to calculate the minimum cost, which is 25. Then cost of okay, 3 2, okay, 3 to cost of 3 2 and cost of 3 4. From this we are going to consider the minimum one, which is 21. Then cost of 4 2 3, we are, okay, cost of 3 to 4 we are considering 25. Cost of 4 comma 2 of 3, in this cost of 4 2 and cost of 4 3 we are going to calculate. Then okay, 25 and 21 we are getting. Finally, okay, we are at last solution. Cost of from 1 to other vertices we are going to calculate the cost. So here minimum of cost of 1 2, cost of 1 3, cost of 1 4, like that we are going to calculate from all these values. Okay, previously already we stored the values. By using those values we are getting the minimum cost is equal to 35. So what is the shortest route here? Shortest route is, okay, 1 to 2, 2 to 4, 4 to 3, again 3 to 1. So this is about the traveling salesperson problem by using dynamic programming. Thank you.